Hello everyone, this is Mr. Couple. In this video, I'll be talking about the history of nuclear fission and the development of nuclear weapons during World War II. Our story begins with the element uranium. Now, uranium is the heaviest naturally occurring element found on Earth. It has 92 protons inside its nucleus. This is what uranium looks like when you dig it up out of the ground in its raw form. And so what scientists were wondering was, could we maybe do something to the uranium nucleus, like shoot a particle at it, or maybe like add protons to it? Because if we could add protons to uranium, we could create a whole host of heavier nuclides. And these heavier elements are called transuranic elements, meaning that they just have more protons than uranium. So the thinking was, what if we shoot an alpha particle at the nucleus? Well, an alpha particle has 2 protons inside of it. So if uranium were to absorb an alpha particle, it would be like a reverse alpha decay. The uranium would gain 2 protons and it would become plutonium. So we would create plutonium. Even though plutonium doesn't exist naturally on Earth, this process could create it. So is there some way that we could do this? The problem is that alpha particles are positively charged, and so is the nucleus of the atom. And like charges repel each other. So this procedure just won't work. We just can't get those alpha particles close enough for the strong nuclear force to take over and bring the alpha particle into the nucleus. So maybe there's something else we can do. So Enrico Fermi has this great idea. He thinks, well, what if we just use neutrons? Neutrons don't have a charge, so they should be able to sneak past the electric field and push in and actually become part of the nucleus. And that's exactly what happened. When the uranium nucleus absorbed a neutron, the nucleus became unstable, and it actually ended up triggering a beta decay to occur, where that neutron was turned into a proton through a beta decay. And he created neptunium, which was the first time that neptunium has existed on the Earth since humans have been around. It was created artificially in a laboratory by bombarding uranium with neutrons. So question 1 is to explain the process Fermi used to create transuranic elements. Pause the video now to answer this question. The next stage in our story is these 2 scientists named Otto Hahn and Fritz Strassman. They were German scientists. So what they did was they took a sample of uranium nitrate and they stuck it inside a box. And then they took this box and they bombarded it with neutrons. And then they looked to see what was in the box afterwards. And so they very carefully unsealed the box and tried to chemically isolate through this complex chemistry process. They tried to chemically isolate the compounds that were inside the box and identify them and see what they were. They predicted that they would find neptunium, just like Fermi said, is if we shoot neutrons at the nucleus, it should become unstable, beta decay, and turn into neptunium. So they were expecting to find neptunium, but when they chemically isolated the compounds, they actually ended up finding, much to their surprise, barium. And this was really confusing because barium is nowhere near neptunium. It's way smaller. It's like half the size. So they were really confused. How the heck did we get barium? We were supposed to be making the nucleus larger. Why did we find something that was smaller? Question 2 is to describe the Hahn-Strassman experiment and what they found. Please pause the video now to answer question 2. So Otto Hahn and Fritz Strassman were extremely confused by this. So they had to send the results off to their colleague, Lisa Meitner. Now normally she'd be working in their laboratory with them, but due to the tensions in the 1930s in Germany, the Holocaust, Lisa Meitner was fleeing. She didn't want to be around Germany anymore, so she was fleeing from Germany for her life. And so they actually had to write her a letter. And Lisa Meitner took one look at the results and said, hello, this is obviously fission. The uranium nucleus is being split apart by the neutron. it's not getting heavier, it's actually breaking into smaller pieces. The reason you found barium was because it used to be uranium. It was broken apart into two fragments. This was the discovery of nuclear fission. Lisa Meitner went on to explain a mathematical model that would show that uranium, if it gets elongated past a critical deformation, which is what we're seeing here, this critical deformation, if the nucleus gets elongated, then the electromagnetic forces can take over and it can rip apart the nucleus. So Lisa Meitner showed that this was physically possible. It's called the liquid drop model. Lisa Meitner also figured out that energy would be released because uranium has a looser binding than the fragments do, since a nucleon has a greater mass when it's inside the uranium nucleus than it does inside the fragments. She realized that this process would end up releasing energy, that the nucleons would each lose mass when this process occurs. You're not changing the number of nucleons, but each nucleon is getting lighter when this process occurs, when the nuclear fission happens. And so she said it would release energy because of Einstein's mass energy equivalence, E equals mc squared. So Lisa Meitner did a whole bunch of stuff. She figured out that fission was happening, she figured out the liquid drop model, and she showed that energy would be released by this process. Unfortunately, and it's a huge blight in the history of physics, Lisa Meitner was not awarded the Nobel Prize for this discovery. Instead, it was given to Otto Hahn and Fritz Strassman. However, this was slightly remedied in the 1990s, long after Lisa Meitner's death, by naming element 108, I believe, named Meitnerium and named in her honor. So she got, the Nobel Prize got stolen from her, but at least we gave her some recognition once we realized what Otto Hahn and Fritz Strassman had tried to take her award from her. Question 3. Summarize Lisa Meitner's discoveries. You might be wondering why I'm saying Lisa, because that's how you pronounce that in German. The E at the end is pronounced with an so Lisa Meitner. So outline her discoveries regarding that she discovered fission was happening. She figured out the liquid drop model, the physical process by which fission occurs, and she figured out that energy was released. Please stop the video now, pause the video now so you can answer this question. Let's recap. So what we realize now is that if a neutron comes in and smashes into the nucleus becomes unstable. It gets elongated to the point where the electromagnetic forces rip it apart. And this process releases energy. Let's remember that there's a barrier to fission, right? Is that the strong nuclear force tries to hold the nucleus together. And so we have to overcome this barrier in order to achieve fission. And the way you do this is by elongating the nucleus past that critical radius, and then the electromagnetic forces can dominate and rip apart the nucleus because the strong nuclear force is limited by the short range. It's the collision of this neutron that causes the fission to occur. But there's a problem, because the neutron, in order to send it at the nucleus, that requires some initial amount of energy. And if we want to actually use this process to really generate energy, well, it's just not going to work, because the energy that it takes to send this neutron with its high speeds at the nucleus ends up being way more than the energy that you get out from this event. And so for the longest time, people were not really worried about nuclear fission leading to the development of nuclear bombs, because everybody knew that it took more energy to send in the neutron than you would get out from this process. So you wouldn't be able to create an explosion of energy through this process. It just wouldn't be possible. However, in 1939, two physicists at Columbia University, Enrico Fermi and Leo Szilard, they figured out that, there's a way around this. They discovered that the extra neutrons that come out after fission, that those extra neutrons can actually go off and trigger additional fission events. So they discovered what's called the fission chain reaction. And it was actually a really funny story. So Leo Szilard talks about when they first did this, they turned on the machine that shot the neutrons. And then they looked and they saw the flashes of light when the fissions were occurring. And then they turned off the machine and stopped firing the neutrons, but they kept seeing the flashes. And so they knew that something was going on, that that initial event was triggering subsequent events, and that's a nuclear chain reaction. So let's talk a little bit about that. I'm going to show you guys this clip from a movie called Our Friend the Atom, which is made by the Walt Disney Company. It's from this TV show called The Wonderful World of Color. This is a clip from season 3, episode 14 from 1957. I just think this is a great video and I want to show it to you guys.
One bullet was used to split the atom, and 2 new ones were created in the process. Now we have 2 neutrons to split 2 atoms. This implied a fabulous prospect, a nuclear chain reaction in uranium. Let's go back to our mousetrap atoms. We can create a chain reaction with them. We'll use our 2 ping pong balls for neutrons. They will be released when the atom splits. Now all these mousetraps are the atoms that will be in the game. They are set, loaded, and ready to go. To start the chain reaction, all we need is 1 neutron. It has to trigger just 1 trap. The ping pong balls that are released will set off 2 other traps. And then we'll have 4 balls flying to trigger more traps. I think you can see what is going to happen. Watch. An atomic chain reaction works in exactly the same way. 1 neutron is enough to start it.
Even though it takes more energy to fire the neutron than you get out from the fission, the chain reaction allows us to surpass that amount of energy that comes out, because all you have to do is send in 1 neutron, and that 1 neutron can cause so many additional fissions that you end up getting way more energy out than you put in to cause it to happen. So if you weren't understanding what's going on here, is a neutron smashes into uranium and it splits it apart into 2 fragments. Usually it's krypton and barium, but really it could be any fragment that's roughly half the size of uranium. And then that spits out between 2 and 3 extra neutrons. It just kind of depends. It's sort of random whether you get 1, 2, 3. Sometimes you don't even get any. And then those neutrons go off and hit additional uranium nuclides. And then those nuclides split. And so now we have a second generation of neutrons. So down here at this table, we're tracking how many neutrons there are at each generation. So in the first generation, in the 0th generation, we started with 1 neutron. And then 1 generation, 1 fission later, now there's 2. So after the second generation, the second events of fissions, now there's 4. And then those can go off and each hit additional uraniums. Now the 3rd generation has 8. And you can see how this very quickly gets out of control in a very short amount of time because it's doubling every single time. And so within about 50 generations, there's billions and billions of fissions happening, and you're just releasing a tremendous amount of energy as you multiply the teeny, teeny, tiny energy that each fission releases times billions and billions of fissions that are occurring within all the atoms in the sample that are fissioning and splitting. So you're not just splitting 1 atom, you're splitting, a trillion atoms. This is question 4. Explain with reference to neutrons how a fission chain reaction works. Please pause the video to answer this question. Fission starts with the neutron, but what ends it? So let's look at this. This is a computer simulation. We're going to send in the neutrons. They're going to hit the uranium. So the uraniums are red and the fragments are yellow. And notice that as they get hit and they split, more neutrons come out. And so the question is, what causes this to stop? Is this just going to keep going forever? Or is there something that ends it? Let's see. Okay, so most of the uraniums have fissioned. We're losing neutrons now. There's no more neutron multiplication happening, and it looks like all the neutrons have escaped. All right, so, we got a pretty good release of energy here. Most of the uranium's fissioned, but a few of them were left over. What if we decrease the number of uranium? So what if we lower the density of uranium so there's fewer of them in the volume that we have here? Let's shoot a neutron at this. And you'll notice now it's much less likely that this neutron is going to hit a uranium. Let's see if it hits it. Oh, it just missed. It's much less likely that this neutron will hit. And so it's almost like it can just miss entirely. Okay, we finally hit. Okay, let's see if we can get a chain reaction going here. Okay, we're steadily going. We got 4 neutrons now. Up, now we're down to 3. Oh, okay, we're back up. What's that? 5? Oh, okay, now we got some action going. Let's see what happens. Oh man, they all missed. No. So that reaction died out. So the middle one sustained itself and kind of kept going at a steady rate. This one we just saw died out. But what if we did this? So what if we had the thing was just filled with uranium? So what if we had a very, very high concentration, a very high density of uranium? Let's see what happens there. In fact, you can imagine what's going to happen. It starts growing uncontrollably to the point where my computer can't even keep up with the simulation, and it starts chugging, and it can't even go at real time anymore. And this thing just completely grows out of control, and in a matter of moments, just completely fissions all the uranium. So what ends a chain reaction? Well, if the neutrons escape the sample, that's going to end the chain reaction. Or all the fission can occur. All the uraniums can fission. And we have names for these different types of masses. So this middle one where the reaction sort of just continues going at a pretty steady rate, that's called a critical mass. So you have enough mass that it doesn't die out, like what happened with the subcritical. The reaction doesn't die out, but it just keeps going. But the supercritical grows uncontrollably and just releases all that energy instantly. And so which of these do you need to make a nuclear weapon? You need a supercritical mass to do that. So keep that in mind. You don't just need a few uraniums. You need a ton and ton and ton of uraniums to turn it into a bomb. For uranium-235, if you have a pure sample of uranium-235, it would be about a 15 kilogram sample for it to be supercritical. So Szilard was really concerned that the Nazis in Germany, remember this is back in the 1930s, the late 1930s, that the Nazis in Germany had figured this out, that they realized that a chain reaction can happen and that you can actually make a bomb out of this. So Szilard was really concerned. He wanted to warn the United States government, but he was worried they wouldn't take him seriously because he was an immigrant. And so he went to his old friend, Albert Einstein, which used to be, he was a student of Albert Einstein's back in Europe. And he asked Einstein to look over the research that he and Fermi had conducted on nuclear chain reactions. And so he asked Einstein if he would review this research and then forward his opinion, his views, to the United States government. And that's exactly what Albert Einstein did. This is the letter that Einstein wrote August 2nd, 1939, addressed to F.D. Roosevelt, the President of the United States. And he just discussed the research that was brought to his attention. So he says, some recent work by Fermi and Szilard has been communicated to me in manuscript. And so basically, Einstein wrote a letter warning the president, hey, you can make a bomb out of uranium, and it looks like the Germans are taking steps to do this if they haven't already done so. We need a response from the United States government that's equal to that. So Franklin Delano Roosevelt writes back, and he says, my dear professor, I want to thank you for your recent letter and the most interesting and important enclosure. So Roosevelt took this warning seriously. Here you have scientists warning the president something bad might happen. And here we have the president actually responding to those warnings and starting the Manhattan Project. And so this is in the late 1930s, early 1940s. The United States starts working to develop a nuclear bomb, and this is called the Manhattan Project. There's a lot of sites that took place. Let me go back. I went a little bit too fast there. There's every single one of these circles is one of the sites where the Manhattan Project took place. And the most important site is Los Alamos, which is what I'm going to show you some pictures of right now. So at the Los Alamos facility, they actually housed scientists. So they brought scientists and their families to live at the facility because they were so worried about leaks that they wanted to actually make sure that the scientists never left the site. So they were kind of locked in there and forced to stay and conduct their research in secret along with their family members living there so that they couldn't be infiltrated by any foreign spies or anything like that. They had a lot of security at the Los Alamos site. They were really, really concerned with foreign espionage, because they're working on a nuclear bomb. They don't want other countries to get those secrets. The Manhattan Project was just huge. There are thousands of people that worked at this facility. I'm just going to scroll across this image just so you can get an idea of the sense of the scope of how enormous this project was and how many people worked on it. Like I said, there are many sites scattered across the country. Two other important sites are Richland and Oak Ridge, which we'll be discussing a little bit later in this video. So at Richland, they were creating plutonium, and in Oak Ridge, they were creating uranium. We'll discuss this in a little bit more detail later on. Most of the people that worked in the Manhattan Project had no idea what they were doing. They were just told to twist this knob or pull this lever. They didn't actually know that they were making the nuclear bomb, that what they were doing was leading towards the development of the nuclear bomb. The project cost about $26 billion in 2016 dollars. It's a pretty large cost. And at the height of the project, they had 130,000 employees. So this is question 5. Briefly explain what the Manhattan Project was and what was the goal of the project. Pause the video now to answer this question. Before we go further into the Manhattan Project, I just want to talk about a few of the obstacles that the scientists in the project faced. So the issue was that the neutrons that come out of fission, they move slowly. In fact, this is a problem because those neutrons can't just cause fission on their own, because they have less energy than they actually need. So chain reaction can only occur with nuclides that fission from slow neutrons. And if a nuclide can fission from slow neutrons, then that means that it can have a chain reaction, because the neutrons that come out are slow. And if you can't fission from a collision with a slow neutron, then you can't have a chain reaction. So there are only certain materials that have this property, that they can fission from the neutrons of other fissions. And those materials are called fissile or fissile materials, which is a combination of two words, fission and missile, so fissile. Here's an example. So if we send in that high-speed neutron at this first uranium, boom, and split it, these slow neutrons come out. A slow neutron can fission uranium-235, but uranium-239 actually ends up beta decaying twice and turns into plutonium. So plutonium-239 is not fissile, but uranium-238 is not fissile. So uranium-238, when it absorbs a neutron, it actually beta decays twice and turns into plutonium. But this is what's really cool, is that plutonium-239 is fissile. So even though 238 isn't, if you just wait a little bit for it to beta decay, it'll turn into something that is fissile. All right, so remember this is really important. Uranium-235 can undergo a chain reaction. Uranium-238 cannot. Plutonium-239 can. Remember these three isotopes, these two isotopes of uranium and this isotope of plutonium, because these two are fissile and this one's not. Here's the problem, and this is what the issue is. Uranium ore, when you dig it out of the ground, it's predominantly, more than 99% uranium-238, which is the stuff that can't turn into a bomb. That's not fissile. And only a tiny fraction of the uranium is uranium-235. So what the scientists had to do was they had to figure out a way to make a supercritical mass of uranium-235. And you just can't dig it out of the ground. It doesn't exist. If you tried to put this rock into a nuclear bomb and shoot neutrons at it, nothing would happen. It would not explode. There's just not enough uranium-235. So if you want to make it supercritical, then you're going to need to filter out or separate out the uranium-235 from the uranium-238. And doing that is extremely difficult because they have the same charge, and the only way to separate them is because of the mass difference, which is really, really tough to do. This device was invented to do just that. It's called the Calutron, named after the University of California at Berkeley, which is where it was invented. So the way the Calutron works is you send the nuclei through a magnetic field. Now first you have to strip off the electrons. So you make sure that they're positively charged. And when a positive charge moves through a magnetic field, the magnetic field exerts a force on it. And so now both of these things are going to have a force on them. They have the same charge. They're going to feel this force from the magnetic field. And that force is going to exert a centripetal force on the nuclei, which makes them move in a circle. And depending upon the mass, they're going to move in a circle with a different radius. And so you notice that this inner path ends up having more uranium-235s on it, and the outer path ends up having more 238s. But it's not a perfect process. So the lighter uranium-235 will bend more because there's less inertia than the 238 does. Here's an example of what that looks like. So you have these guns here that fire out the mixture of uranium nuclides through the magnetic field. It bends them, and you have this really teeny tiny path difference between them, and you end up trying to scoop up and filter out the two different tracks here. What you do then is once you've filtered this inner track, and this is way exaggerated, there's really not that many uraniums on this inner track, but you filter out this inner track and then you send them to another machine in a row. And so each of these machines, like each of these blocks, is a calutron. So the calutrons look like this down here. And so each of these blocks is a calutron. And so you just take the output from one and feed it into the next one, and you just run this, and it just keeps cycling and cycling. And eventually what's left after a really long time is you end up taking that 99% uranium-238, and 2 years later, you've turned it into weapons-grade uranium, which is 90% uranium-235. So you've gone from less than 1% 235 to the sample being over 90% uranium-235. And now you can put that in a nuclear bomb, shoot neutrons at it, and then now it'll go off. But you want to make sure that it's always subcritical. So it's not large enough of a sample yet. Most of the neutrons are going to escape this sample. When you want it to explode, you have to do something special to get it to explode. We'll talk about that a little bit later. All right, now here's the thing. That was at Oak Ridge where they were doing the calutron stuff. Now, the Hanford B Reactor, which was up in, where was it? Hanford, up in Washington. What they did here was they actually took a little bit slightly enriched uranium. So it has a little bit of extra 235s. Those are the red ones. It has a little bit of extra uranium 235s. And what they're going to do, I think it's about like 10% or so uranium 235. So it's not less than 1%. So it's been enriched a little bit. They run it through the facility at Oak Ridge. But then they stick this in this thing called a reactor. It's called a breeder reactor. And they shoot neutrons at it and watch what happens. The neutrons come in, and as long as they hit a 235, they'll split and cause more fissions. But remember, when the 238 absorbs a neutron, it turns into plutonium. But you can imagine if you keep running this reactor, what are you going to be left with when it's done? Is you're going to be left with a bunch of plutonium. And so this reactor actually creates plutonium. And so this is the way that they acquired the materials during the Manhattan Project, was they used the calutrons at the Oak Ridge facility in Tennessee to refine uranium-235, the fissile material, and then they used the Hanford B reactor to create plutonium in the breeder reactor. And so what we find is that it's really difficult to acquire uranium-235 because you have to actually separate out the 235 from the 238. Remember, the 235 is very rarely found in nature. That's the stuff we need to make the bomb. Most uranium is 238, over 99%. So you actually have to spend a long time separating out. It's really difficult. It's really energy intensive and technologically intensive to do this. Whereas on the other hand, all you have to do is just stick some uranium into a reactor and you can create the plutonium from the abundant uranium-238. So there's all this 238, you just shove it in the reactor, shoot some neutrons at it, and then it'll turn into plutonium-239. And this is why nuclear reactors are scary, like when countries start to use nuclear power, because the same process that generates electricity inside a nuclear power plant can create plutonium. There is no risk of nuclear power plants exploding like a nuclear bomb. That's completely wrong because you never have that 90% supercritical mass. But there is a risk of nuclear materials being created, that the uranium-238, this is the way that you can create and turn it into plutonium. So every nuclear power plant has the capability of creating plutonium, which can then be used to make a nuclear bomb. However, uranium-235, even though it's really hard to enrich and refine, it's stupid easy to turn into a bomb. Whereas plutonium is really difficult to turn into a bomb. So no matter which route you take, whether you decide to make your bomb with uranium or with plutonium, you're going to run into some difficulties. It's super easy to turn a bomb into uranium. All you have to do is just use this simple cannon device where you take two subcritical chunks of uranium and just blow up a bomb and then send it, boom, this bullet gets shot down this barrel and it smashes into the target. And then when those two combine together, now the mass is supercritical, and now it has enough that the neutrons don't escape anymore, and the thing will actually blow up. So as soon as you combine these two chunks together, the thing blows up. Now, plutonium, unfortunately, if you try to do this design with plutonium, it won't work. The plutonium is way more unstable, and it will actually sort of just fall apart before you can even get them pushed into each other. The plutonium does what's called spontaneous fission, so it's really difficult to get plutonium to not just, slowly, gradually fall apart, fission apart on its own, even when it's hard to initiate it. So to do that, to create this plutonium bomb, they actually had to put a thin shell of plutonium, and then they had to compress the shell, because you never allow there to be enough plutonium in one place that it will trigger a chain reaction. So you want to make sure that there's a thin shell of plutonium, and then you just implode it. You just compress it inward through conventional explosions. This is a really difficult process to do. It's highly complex, and there's a lot that can go wrong. If your measurements are just slightly off, this thing will just completely fail, and it'll be a dud. So whichever way you go, you're going to have difficulties. With uranium, the difficulty is in acquiring the material, whereas with plutonium, the difficulty is in actually constructing the bomb. So question 6 says, outline the difficulties with making nuclear weapons. Pause the video now to answer this question. I want to show you some actual pictures of the Trinity Test, which was the first plutonium test that the United States government conducted during the Manhattan Project. Now, it took 2 years to get enough uranium to make one bomb, so they actually never tested the uranium bomb. They were so sure it was going to work that they didn't feel like it was worth wasting all of the uranium that they'd spent 2 years creating to test to see if it would work. They just assumed that this is a foolproof method and it would work. But the plutonium device, that needed to be tested. So this is the plutonium core of the bomb. You can see for size, it's inside this container. This engineer is holding, or scientist is holding it. And then you take that core out to this is the actual device itself. So that core is inside here. So this is the highly complicated mechanism that's going to trigger those explosions or rather the implosions that compress that core. And when they compress the core, it becomes supercritical, and then it can explode. You take this device, they lifted it up on top of this tower. Here's a picture of the device on top of the tower ready to go. And they just set up the timing configurations, and then when they push the button, the devices would go off, they would implode the core, the neutrons would fire, there'd be a supercritical mass, and the whole thing would explode. And so here's a video test footage of that happening. Now remember, this was in the 1945, so this is some super old video here, so it's not very high quality. This is also extremely slowed down footage of the actual explosion of the Trinity Test, the very first nuclear explosion ever in the history of humanity. Massive release of energy. In fact, after the bomb went off, you can see this giant crater that was left over in the desert, that just massive amount of damage and destruction that was caused by that teeny tiny little core that the guy was holding in his hands. When they went to the site afterwards, that this is all that was left of that tower, the tower that they lifted the bomb up onto. It's completely gone. You might be wondering, are they safe going there? It's not too dangerous. You'll notice that they're wearing these little booties. The thing that's really scary is if you get these radioactive fragments, because the fragments that are left over after fission are highly radioactive. If you get those fragments on your clothing or on your hands and carry those back with you, you can get some long-term exposure to radiation. But just visiting the site is not that bad. They don't have to worry too much about it. But obviously, they shouldn't be there. It's kind of stupid. They just didn't really know too much about it back then. But at least they're wearing the booties, so they know that wear those little booties so that they don't carry the isotopes, the radioactive material, back with them on their clothing. The explosion was so hot that it actually melted the sand of the desert in New Mexico. It melted the sand into glass, and it created this material which people call trinitite. For the Trinity explosion, they call it trinitite. You can actually, I think there are like museums that have this on display if you go to the New Mexico desert, to where the Los Alamos facility is. Here's another close-up picture of the trinitite. So 2 bombs were built in the Manhattan Project. The Little Boy bomb, which used the uranium-235, you can see that it's called Little Boy because it's this skinny design, because it had to fit that barrel that they shot the bullet down. And then this device is called Fat Man. You can see it's much larger because it had to have that spherical implosion device within it. So 2 bombs were built and they were used. On Hiroshima was Little Boy, and Nagasaki was the Fat Man bomb. This is a before and after image showing you the destruction that these bombs wrought on the Japanese targets. Back in 2009, that should say 2009. Back in 2009, I actually took a trip to Hiroshima. I teach this all the time, and I thought it'd be important for me to actually go and see it for myself. This is the atomic dome. This is a famous landmark that they've kept. The Japanese people have kept it in its destroyed state. You can actually see their scaffolding up here when I went about 10 years ago, because they're actually trying to repair the ruins so that the ruins didn't fall apart. They want to preserve this building in its blown out, destructed state as a reminder of what took place here. It was a hotel. It was one of the most high-tech, advanced, modern hotels in Hiroshima when it was built. And then this is what it looked like after the bomb went off. The bomb actually went off just above this building in the air. They actually blow up the nuclear bombs in the air because they have a higher destructive yield when you blow them up in the air. So I walked around the site where this memorial was. It's just a beautiful, beautiful city. You look around, it looks like nothing even happened, even though, a little over 50 years before this, the city was completely destroyed in a nuclear bomb explosion. Here's some famous pictures that you've probably seen. This picture, there's shadows being cast by the bomb. So the bomb was so hot and so much energy and radiation came out that it actually scorched the ground. And so places where these posts were actually ended up casting a shadow because the light from the bomb exploding wasn't able to reach those spots. So all the other places ended up getting scorched except for these shadows that were cast by these pillars. And these shadows are etched permanently into the concrete bridge here. This is also all that's left of the human remains of a person who was sitting on these steps, and then they were supposedly vaporized by the bomb going off. It's quite horrifying stuff. But as I said, Hiroshima looks like a totally normal city. Nothing happened there. My uncle used to live there for a couple of years. I mean, it's a thriving, massive, populated city. And they don't have to worry about radiation exposure because they actually took a bunch of bulldozers right after the bomb went off, and they removed the top 6 feet or so of soil and just shipped it away. And so now all those radioactive fragments are gone, and you don't really get any more radiation exposure in Hiroshima than you would in any other city in the world. I walked a little bit further and I found this place called the Hiroshima Peace Museum. And when you walk into that museum, they have this giant diorama showing you the aftermath of the nuclear bomb explosion. This red sphere is showing you where the bomb actually detonated, where it went off in the air. And then there's that hotel that you saw earlier, the atomic dome. And you can just see this widespread destruction where the nuclear bomb just completely annihilated this whole city. And I just walked around the museum and it was just shocking, the level of detail, and just stunning. It just made everything real. It wasn't just something that you read about in the history books. It was real to me. It was moving. It was horrifying. It was just crazy. It became something that actually happened, that people were actually affected by this. And it wasn't just something of America, let's win the war. It was whoa, we did something crazy. People died. People were mutilated. People had the skin burned off their bodies. This is horrifying. There's one statue that I found. It was dedicating this young girl. Her name was Sadoko Sasaki. And there's actually a book that many of you have probably read. But I found this statue outside just commemorating her. She actually died of radiation exposure of cancer, leukemia that she got, ended up killing her, that she got from the bomb going off. And this statue was commemorated in her honor. There's a Japanese legend that says if you fold 1,000 paper crane origamis, that your wish will come true. And so she tried to fold 1,000 paper cranes to cure herself of this illness, but she never made it. And so now, every year, I'm starting to cry, guys. Every year, students from around Japan will fold paper cranes and bring them to this memorial site and put them up on display. And I just thought this was just a spectacularly amazing, beautiful memorial, even though it's horrifying. But yeah, this inscription on the statue says, "This is our cry, this is our prayer, peace in the world." So they've turned this horrible event into a call for peace. Question 7, reflect, write down your thoughts on what has been discussed. Pause the video so you can answer this question. Okay, I want to show you guys some images of bombs going off, and the best videos out there is this movie from the 1990s, which was what my high school physics teacher showed me back when I was in physics back then. I took physics in 1997 to 1998, so this movie was brand new, and my teacher showed it to us. It's called Trinity and Beyond, the Atomic Bomb movie. So this is some weapons test footage. I'm just going to let this video play out, and then you guys can experience what I experienced when I was in high school. So nuclear bombs release a tremendous amount of energy, and it's not the radiation that causes the destruction. It's not any like special nuclear stuff that causes the destruction. It's actually just the pressure wave that's created from the bomb exploding. And so you can actually see that this pressure wave just rips apart this house. Like this incoming pressure, just this wind just boom, blows apart this house. You can also see look at how burned and torched this trailer is. Like it's been scorched by all the radiation. The light that's released from the bomb just is so hot and so much heat that it just scorches this trailer. This metal trailer gets completely scorched. So the two things that are damaging in a nuclear bomb are that blast wave, that pressure wave, and then also the tremendous heat that gets released from the bomb. So the question that students always ask is, well, what would happen if Sumner was nuked? So I thought I'd show you guys what would happen if Little Boy was dropped on Sumner Academy. So this is if it was detonated in our classroom. This is actually in my classroom in room 101. There's a little demo table at the front of the classroom. And imagine if we just stuck this bomb on that table, this is what would happen. This map is color-coded, showing you the various effects that will happen. So if this bomb went off in the middle of the day at Sumner Academy, you'd expect about 12,000 fatalities and 22,000 injuries from Little Boy. The yellow circle in the center, that's the fireball. So anything within that range gets instantly vaporized. It's so hot that the molecules just instantly turn into a gas. Any solid molecules becomes gas. Next is the air blast. And so that's air blast 1. So air blast 1 will destroy pretty much any building, except for like the strongest concrete buildings, but pretty much any building will get destroyed within that red radius. Next, we have the radiation. This is a lethal dose of radiation. If you're within this green area, you'll have a lethal dose. Now, the only reason that this radiation is here is because it was a ground detonation. If we actually detonated this in the air, the radiation would be almost non-existent, unless there is some conditions of fallout, which is where the radiation can fall back down to the ground. But that depends on winds and stuff like that, so we're not going to model it in this simulation. Air blast 2 is this gray line here, and any wooden structure, and most houses are made of wood, any wooden structure will get destroyed by air blast 2. That's what you saw in the video of that house getting blown apart. That's air blast 2 in this radius here. So anyone within that radius, your house is going to get destroyed. The last circle there is third-degree burns. So if you're outside with a line of sight to the bomb, so you can't be in any shadows, but if you have a line of sight to the bomb, your skin will burn off your body if you have a direct line of sight to the bomb, if you're in this circle here. If you go beyond that, there'd be some rumbling. You'd probably get some like lower degree burns. Buildings will get damaged, maybe like in a severe thunderstorm type damage, but it wouldn't actually destroy the buildings. But in this inner rings here, this is where actual complete destruction and devastation lies. We've gotten scary good at making nuclear weapons in the last 50 years. This is a modern thermonuclear warhead. So we actually realized that, you can create two different warheads within the same bomb. So one bomb is a fission bomb of uranium, and it can trigger a fusion bomb of hydrogen. And so that's it's deuterium. Do I see deuterium? Where is deuterium right here? So deuterium and tritium, that's hydrogen. Deuterium and tritium, those are hydrogen 2 and hydrogen 3. So you have your fusion bomb here, and fusion releases way more energy per kilogram than fission does. And then over here you have your uranium bomb. And so the uranium bomb is so energetic and creates such high temperatures that you actually start to be able to fuse hydrogen together to create even more energy coming out of this thing. So it's taking advantage of the two processes we learned about that release energy, fission and fusion, to make the most destructive bomb ever. This is what would happen if we dropped Ivy Mike, which was the first fusion bomb This is what would happen if we dropped it on Sumner. And you can see that that area of destruction is just ridiculously amplified because we're not just using fission anymore, but we're also using fusion. And fusion per kilogram is way more energetic. But remember, it's two bombs. It's a fusion bomb and a fission bomb. So it's like this, it's just massively destructive. So if this bomb, Ivy Mike, this is the largest bomb the United States ever developed, it would be 248,000 fatalities and 389 or 390,000 injuries. Okay, next, this is the largest bomb that was ever made. It was made by the Russians. It's called Tsar Bomba. This is what the Tsar Bomba would do. So modern nuclear weapons are just extremely scary. You know, we've never detonated anything of this size on a city before. In comparison, Little Boy only killed a few city blocks. This is taking out the entire Kansas City metropolitan area. I mean, it's even reaching all the way out to Lawrence. Like, this is just a massive, massive area of destruction. And this is what people are so scared about when you hear about nuclear weapons, is that modern nuclear warheads are insanely powerful and can destroy entire cities. This bomb would cause 740,000 fatalities and 605,000 injuries. I mean, you're looking at pretty much every single person in the Kansas City metro area being affected by this bomb. In fact, Mr. Gibson likes to talk about how the crater that's left behind would become a lake because all the rivers are feeding into this, and then you'd end up creating like a Kansas City lake. This radioactive remains of Kansas City would be a lake. He also talks about how the highways were built to go around this. If this were to happen, if Kansas City were targeted, that the highways could actually allow you to still circumnavigate the city, which is what he says why the highways are built that way. Interesting theory. Okay, so what do we use today? So we use these are called MIRV, so a W87 MIRV. This is what one of those. So see this triangle? Remember that picture I showed you a few slides ago with that cutaway picture of the different cores? So there's two nuclear cores inside here. This one little triangle is one warhead. So what you do is you load up a bunch of these warheads, each one doing 50,000 fatalities on Kansas City, destroying this entire area. You load up a whole bunch of them onto an ICBM, you launch it up into space. It's called an intercontinental ballistic missile. It's ICBM. You launch it into space. This thing goes up into the atmosphere, breaks apart into the independently targetable, comes down and rains this destruction across the city. So this is called a MIRV, M-I-R-V, multiple independently targetable reentry vehicles. So your rocket goes up into space, breaks apart, and then each of these warheads rains down on a different target. This is what it looks like if it were coming down. So, you know, we've tested out the MIRV. We actually didn't use armed warheads, but these are the trails that come down. So each of these locations, each of those locations has an explosion that big. And so this is what ends up happening. That one ICBM going up can actually end up spreading out the destruction over a much larger area. So you realize that it was much more efficient to nuke a bunch of different spots repeatedly with multiple warheads than it was to just launch one big old warhead. And so this is the bombs that we now use today. And so you can see that this is actually as destructive as the Tsar Bomba in terms of fatalities and injuries, but it's a much smaller area of effect. So these are much more targeted, much more precise, and way more damaging and deadly than that big Tsar Bomba, which is why we've moved away from the large nuclear bombs and switched to these rocket-based, or I shouldn't say rocket, but intercontinental ballistic missiles. So they're put on a rocket and launched into space. And you can send these, they're called Minuteman rockets because you can launch them within a minute. So if we detect an incoming attack from another country, we can within a minute retaliate against them. And so this is the only reason why you're alive today. It's something called mutual assured destruction, that we've developed weapon systems where we say, as soon as we detect a launch against us, we will launch against you. So if you try to kill us, you'll be only killing yourself. And that's the only thing that has kept us alive for these past years. Okay, that's it for this video, guys. I hope you have a great day. Sleep well tonight. I know this stuff is really scary, but there it is. All right, I'll talk to you guys later. Have a great day.